Today we're going to take a look at half of section 7.3. Now, in section 7.3, we're going to look at the inverse of an exponential function, which happens to be the logarithmic function. So our objective for today is to write equivalent forms for exponential and logarithmic functions. And then we're going to write, evaluate, and graph logarithmic functions. Okay, so when you're all done today, you're going to be able to take an equation like the one that I've showed right here, log of 9 base 27 equals 2/3, and write it in exponential form, and vice versa. Before we get started here today, I want you to do these two problems and try to do them mentally. Alright, go ahead and pause the video and work through these two. Okay, now that you've worked through these two, first of all, you had to remember negative exponent meant reciprocal. So it was simply 1 over 4 cubed, or 1 over, yep, you said it, 64. Alright, on the second one, it's going to be to the negative 5, 10 to the negative 5, which means it's going to be 1 over 10 to the 5th, which is 1 over, let's see, a 1 and 5 zeros, so 1 over 100,000. Or you could write it as decimal form, and it would look like that. Alright, so let's get started here with today's. There are 3 vocabulary words we're going to be taking a look at over the next couple days. The first one is a logarithm, the second one a common log, and the third one we're going to learn about a logarithmic function. Okay, so let's get started. We're going to introduce logarithms through this example. Now, in looking at this example, let's read it together. And it says, how many times would it take to double $1 before you had $8? Now, what I'm going to do is I'm going to use the formula that we had before. So we know that a sub t is equal to lowercase a, which is the initial amount, times b, which is your rate, raised to the t. Alright, now, looking at this question, first of all, we have $1, so we're going to plug in a 1 for a. We see that it doubles, there's our rate, so it's going to be times t. And it says how many times, okay, that's our t. So I want to know how many times it has to double before it actually equals, and our amount after t times is 8. Now, looking at this question, is it possible with our current knowledge to solve for t? And the answer is no. Okay, it's not possible. So that's where it comes in. We have to learn a different type of mathematics, a different rule, okay, different properties. And those properties are called logarithms. So on the right side of your paper, we're going to put this definition here. On the left side, if you would please write log. Okay, so on the left side, put logarithm. And on the right side, you're going to say a logarithm is the exponent to which a specified base is raised to obtain a given value. Okay, again, a logarithm is the exponent to which a specified base is raised to obtain a given logarithm. Alright, go ahead and pause it and get down that definition. Now, before we move on to the next slide, I want to point something out here. Notice in this problem, it says, how many times would you have to double 1 before you had $512? Okay, so, in other words, you have 2 to the x. Remember, that's 1 times 2 to the x equals 8. Now, by using the inverse operations, you could undo raising a base to an exponent equation to model the situation. And that's what we're going to do. In other words, we're going to convert from exponential form to its inverse, which is the logarithmic form. So let's take a look at how we would do that. Alright, here's the rule that we're going to be using. Using this rule, notice the base of the exponent becomes the base of the log. Notice that your exponent here is what it equal to is over here. And notice your a value here becomes your a value there. Now I have a little saying that's going to help us remember. The base of the exponent becomes the base of the log. And the inside, notice this is the inside, it's with the b, and the outside are going to switch places. In other words, the x goes outside and the a goes inside. Okay, so all together, the base of the exponent becomes the base of the log, and the inside-outside trade places. Alright, now let's practice some problems using this rule. Okay, here are some questions. 3 to the 5th equals 243. Well, in taking a look at that, right there is my base of my exponent. So the base of the exponent is going to become base of the log. So that means I'm going to have log. It's going to be base 3. Okay, and the inside-outside switch places, which means my exponent is what it is equal to, and I'm going to take the log of 243. So log of 243 equals 5. Alright, now you try the next one. The next one, it says 25 raised to the 1/2 equals 5. Okay, so what's the base of the exponent? Yes, 25. So that's going to be the base of my log. And then the inside-outside switch places, so the 5 on the outside goes to the inside, that's right. And the exponent is what it is equal to. Alright, very good. So here's what it's going to be. Okay, now you go ahead and try the next 3, and then we'll talk about it here in a moment. So go ahead and pause it and you do the next 3. Okay, let's check it. Here's what you should have received. For the first one. Now, this next one here is a little tricky because you had to remember x to the -1. And remember, when you have x to the -1, that's the same as, yep, 1 over x. Okay? So, but you can use the same thing. The 6 is the base of the exponent, so it becomes the base of the log. Inside, outside, switch places. Okay, so this is what you should have. And for the final one, that's what you should have. Okay, how are we doing? Alright, let's go practice some more. Alright, go ahead and pause it, and you work through these 3. Notice on the last one, x cannot equal to 0 because you can't have 0 to the 0 power. Okay, go ahead and pause it and do these 3. Alright, let's check it. On the first one, did you agree with me? Here's the second. And the third. Alright, I think we're getting good at these. Okay, look at these. Now, notice here, we are given the logarithmic form this time, and now we have to go to the exponential form. So, same type of rule. Notice the base of the log becomes the base of the, you said it, the exponent. And then the inside, outside trade places, which means the 1 becomes the exponent. So the logarithm is the exponent. Okay, so let's go ahead and work through the first one here. Okay, so I see this 9 right there becomes the base of the exponent. And this logarithm here becomes the power, so 9 to the 1st, so the outside becomes inside. And of course, right here, the inside goes outside. Now notice, is that true? 9 to the 1st power, does that equal 9? Yes, it does. Okay, so now, I'm going to let you do the other 4 here, and then we'll talk about it here in a moment. Okay, let's take a look at the first one. What'd you get for the first one? Well, let's see here. You have a 2 for a base. So that 2 becomes the exponent. And the inside-outside switch places. So there's what you have. Okay, again, here you see the 8 is the base of the log, so it becomes the base of the, yep, that's right, the exponent. And then the inside-outside switch places, and you should have that for an answer. Okay, now for this next one, same type of thing. Let me just uncover these and let's check them. Very good. And the last one. Very good. Now notice it says b to the 0 power. Well, what do you know about anything to the 0 power, everything except for 0, of course, to the 0 power equals 1, so it comes out a true statement. All right, very good. In this slide, let's review. Remember, a logarithm is an exponent. So that means your properties or your rules of exponents also apply to your rules of logarithms. All right, so let's take a look at two special properties of logarithms. And the first one says this: if I take the log of any base b of b, it equals 1. In other words, if your base of the log is the same as what you're taking the log of, b, it always equals a 1. Now, why is that true? Well, let's convert it to exponential form. So the base of the log becomes the base of the exponent. Inside, outside, trade places. B to the first power equals b, and that's true. All right. So notice over here, if I take a look at, I have the log of base 10 of 10 equals 1. So when the base of this log is the same as what's right there, these, in a sense, and I have a little saying, log out, leaving us with just 1. Okay, now why is that true? Well, think of it like this. B to the first power equals 10. Okay? B to the exponent of 1 equals 10. Alright, now let's take a look at the second property. The second property says this: the log of 1, any base you want it to be, doesn't matter if it's 2, 3, 10, or 45, doesn't matter what it is, equals 0. Why is that true? Well, let's convert it to exponential form. The base of the log becomes the base of the exponent. Inside, outside, trade places. B to the 0 power equals 1. Is that a true statement? Isn't it true that anything to the 0 power except for 1, that is, except for 0, that is, anything to the 0 power except for 0 equals 1. And that is true. Okay, for example, 5 to the 0 is 1, 10 to the 0, 1, 2 million to the 0 is 1. Okay, so anything to the 0 power, except for 0, of course, equals 1. Okay, so over here, here's our example. Log base 10 of 1 equals 0. All right, and why is that true? Because 10 to the 0 power equals 1. 10 to the 0 power equals 1. Very good. All right, now let's go apply some of these rules to some examples. Before we go into some of our examples, let's first get another definition. The definition here is common log. So on the left side of your Cornell notes, I want you to write common log. And on the right side, common log is a logarithm with base 10. It's a logarithm with base 10. Now, what that means is this. If I were to have log base 10 of a 5, oftentimes I would not write it with base 10 right down here. I would just write it as log of 5. So if you don't see anything there, what does it mean? Well, that means your base of your log is 10. As we look through these next few examples, let's try to do some mental math. Now, keep in mind, we just talked about a common log. Do you see right here a base of the log? And since you don't, what does that mean? Well, yes, that means it's base 10. Okay, now notice I don't see anything over here either. So we have to just kind of ask ourselves, 0.01. So let's do some mental math. Isn't 0.01 the same as 1 over 100? And isn't that the same as 1 over 10 to the second power? And isn't that the same as 10 to the negative 2? Alright, so that means I'm going to convert it from log to exponential form. So I'm going to take the base that we don't see, which is 10, raised to the what power, and that is going to equal 0.01. Okay, and that's what I have right there. Alright, so 10 to the what power equals 0.01. Well, you know what? I think we've already found out what that is. Isn't it negative 2? And yes, it is. It is negative 2. So, there we go, which means that is equal to negative 2. Okay, here, mentally do this problem. Go ahead and pause it and mentally see if you can figure out what is log of 125 base 5. Now, some things I want you to remind you of. This is equal to what? Okay, so we'll draw a question mark there, and go ahead and convert it from logarithmic form to exponential. And when you do that, you'll have your question mark. Alright, so let's take a look at what we have here. So, today we have, okay, 3. Did you get a 3? Excellent. So that tells us that the log of base 5 of 125 is 3. Okay, let's go to our next. Okay, this is going to be the last one we're going to play with here today. So, remember here, okay, this is equal to a question mark. Okay, also remember 5 to the negative 1 equals 1 over 5. Okay, that's enough hint. Alright, you go ahead and pause it and work it out. Okay, what'd you get? Yes, let's see here. You have 5 to the what power? Negative 1? Good, I agree as well. Negative 1. We have one final thing we're going to look at. So let's, on the left-hand side of your Cornell notes, I want you to put logarithmic function. Now, what we're going to do is we're going to find the inverse of this exponential function right there. So if I were to step through the rules for, the process rules for finding the inverse of a function, remember the first thing I do is I replace f of x with y. Okay, it's already done. Then I'm going to interchange x and y. Okay, so I have x is going to equal 2 to the y power. Alright, now we have to solve for y. Up to today, we couldn't do that, but now we can, now that we have logarithms. So, first of all, the base of the exponent becomes the base of the log. See that right there? And then the inside, outside, trade places. So the exponent becomes the log, and this x here goes right there. So we have y equals log of x base 2. Now, what does that function look like on the graph? Well, remember y equals 2 to the x looks like this one right here. So if we reflect that over the line, y equals x, it looks just like this. And this right here, the graph that I'm tracing right now, is my logarithmic function. But we're going to study that more next time. So let's wrap this up for today. Okay, folks, let's recap what we learned today. The first thing that we learned was to change exponential into logarithmic. So that means the base of the exponent becomes the base of the log, inside, outside, trade places, and we're left with log base 6 of 1296 equals a 4. Alright, now let's take a look at the next one here. The next one here we changed it from logarithmic form to exponential form. Again, the base of the log becomes the base of the exponent, inside, outside, trade places, and I'm left with this. And then we did some mental math. And in playing with the mental math, and we'll just take a look at the first one here for time's sake here. Looking at the first one here, notice you do not have a base here. So if you don't see a base, that means it's common log, which means that base is, yeah, you said it, it's going to be 10. So 10 to the what power equals 100,000? Yes, 10 to the 5th power. And there it is. And just for the sake of the next two, if you guys wanted to play with those, this is going to equal 0.5, and this one's going to equal -3. All right, now, let's get this lesson wrapped up. Okay, students, that wraps this up for today. Here's your problem set. Go ahead and write that down. Don't forget to write down your summary. And for the sake of doing it, let me give you a little quote. And I want you to make sure this quote gets into your summary. So as Porky Pig says, yabbity yabbity yab, that's all, folks.